All right, we've got an alignment here, and it's 60 nucleotides in length. We've got 4 sequences. We've got the reference and then 3 other samples labeled S1 to 3. And straight away we can kind of see that most of the sequence is exactly the same. There are a few differences, which you can see here and here. Let's just highlight those to make it easier to see. So we can look at this and identify straight away what are the positions which are different. And really, we are probably mostly interested in differences. So in this case, we could easily store this, and it's fairly small, but in the context of a human genome or a large bacterial genome, it's probably not efficient to store everything that we see for each sample. So instead of that, what we can do is we can simply just store the positions which are different from the reference, because we know the reference sequence and we can easily see then what the differences are. So for example here, we can see that the sample 1 has got a difference at position 14. Here, sample 2 and 3 have got a difference from the reference at position 23. So a very simple way of storing this information would be in a simple kind of table. So if we, everything we need to reconstruct this alignment, what we need is to obviously know what the reference sequence is. So if we store that and then create a table which can allow us to reconstruct what sample 1 to 3 were. So in this case, all we need to do is store the position, and then sample 1, sample 2, and sample 3 will be our columns. In this case, let's start with position 14. Sample 1 is an A, and sample 2 and 3 are T's. Sorry, are C's. In this particular position here, sample 1 is T, sample 2 is T, and sample 3 is the same as the reference, which is G. So using this information and our knowledge of what the reference sequence is, we can actually reconstruct this very easily. So one extra kind of information which might be useful is to know which of these are reference and which are different from the reference, because just looking at this we don't know unless we have the reference sequence with us. So something that we could add is a column denoting what the reference position, what the reference allele is. So here we can mark this as C, and we can mark this as G. So again, this is quite a simple table. It's very easy to see. What else can we do? So someone might ask you, give me all of the positions and all of the reference alleles. And in this case, what we can do is we can add an extra column and provide all of the alternate, so non-reference alleles present in our samples. So in this case, there'll be just one, which is A, and in this case, there'll be another one, which is T. So very simple, without even looking at all of these columns. Obviously, we don't have that many samples here, so it's easy to do, but if we have thousands, it might be quite difficult to identify what the alternate alleles are. In this case, we can just store it in one column. It's very easy to see. And similarly, if, for example, we change this so that maybe this is a G, now the situation has changed, so we can make this a G, and our alternate, we just add a little G in here. Okay, so now what happens if we add some insertions into the mix? So for example, if all of our samples have an insertion, what we can do is we can just remove this, and now we have an insertion here. So at position, or between positions 31 and 32 in the reference, we've got an insertion of a C. Okay. So we can also record that. So the way that we can record this is basically saying because we always need the reference position, but this doesn't have any position in the reference. We can use the position before it. So in this case, what we can say is 31. The reference allele is just A, and the alternate allele would be AC, denoting that there's been an insertion. Sample, and all of the samples have this, so put it like this. So that's all fine for just a simple insertion, but what happens if the insertion is quite large? So for example, if I change this to remove a larger segment, we can still put this into our file or into our table. Something like this. So, okay. So here we'll change everything. Obviously, it's quite large, so let's make these a bit bigger. And straight away you can see already kind of we're running into issues just with Excel, just having to resize things. But more importantly, if this file is quite large and you have hundreds of thousands of variants and hundreds of thousands of samples, each of the characters basically increases the file size and increases kind of processing time on anything that you want to do on the file. So you can imagine this is still very small, but sometimes you have quite large insertions. So a more kind of space efficient way of storing this would basically be to code the alternates with a number, and then for each sample which has that particular alternate, just use that number. So for example, we have just one alternate here, so we can code this as 1 because it's the same as the alternate, 1 and 1. We can do the same for these. So we code the alternate as 1 if it's one of the alternates. Now here, this is actually the reference allele. So what we do here is we code it as 0. And here, it's an alternate, but it's not this. It's not an A, it's a G, which is the second alternate. So in this case, we use 2. And then here again, alternate, which is 1, alternate 1, and 0. So now actually, you can see that the number of characters that we've used in the entire table is a lot fewer just by changing to this numbering scheme. Okay, so some of the interesting things that you might want to do is to filter this particular variant matrix. And let's say we just want to take only the rows or the positions at which all of the samples have an alternate allele. So obviously we can kind of look through each one and quickly see that this is the only allele or the only position which we should take forward. You might decide at one point to do a certain kind of threshold of 1 or 2, and then maybe later you want a different threshold. So to avoid us having to look through all of this, what we can do is just compute once the number of alternate alleles, and then kind of just note that down as a separate column. So let's just make this a bit bigger. We can calculate the allele count. In this case, it will be just 2, because we have 2 alternate alleles here. Here again be 2, and here 3. So if we want to filter and only select those at which, actually let's flip it around. If we only want to select those at which there's a kind of a mixture of alternate and references, then we want to exclude this because all of our samples have the same allele. And usually that's not so important in studies. So let's filter this. We can basically say anything that's not a 3. So here we've got our interesting variants. Another way of going kind of around the same kind of filtering is to use the frequency. Quite often we're more interested, especially when we have lots of samples, in a minimum kind of frequency cutoff. Usually in human studies that'd be 5%. So let's include all of our samples again. So instead of allele count, alternate allele count, we can do alternate allele frequency. So here, let's just make sure it's a number. What we can do is we can do, this is 2 to 3, 2 alternate alleles over 3 possible samples. Here again, it's the same. We've got 2 alternate alleles, that's 2 to 3. And then here we've got all of them are alternate alleles, so it's 3 over 3. So here we could do a similar kind of frequency-based filtering. So what is that? Everything that's less than 1, for example. So here we can see we only have our 2 chosen interesting alleles positions. So we can keep actually adding in extra annotations. Here we've just added in 2. Some other things that you might be interested in is maybe what gene is it in. So this particular position, what's the gene that it falls into. So we can start saying, all right, it's we'll do a B, for example. They're all pretty close. Let's just make them all the same. What other things are we interested in? So let's just say, let's convert this to protein. Right, so here we can see that these actually lead to amino acid changes. So the reference here is a P, in sample 1 is H, in sample 3 it's R. So we can start annotating that. So let's call that protein change. So let's just make this, it's 1, 2, 3, 4, 5. So that's P5H. We do have an other alternate, so we can, in the same way that we've annotated the alternates with a comma, we can always do this in the same way. So this will be P5R to make sure that the order is the same. So we instantly know that sample 1, which is alternate 1, which is A, has this change here. Sample 3, which is alternate 2, has this change here. Okay, let's look at the next position, which is here. This is a glycine to valine. Position 1, 2, 3, 4, 5, 6, 7, 8. Glycine to valine. Obviously here it's a bit more tricky. Let's just ignore this for now. So maybe we can denote a special character for any information which we don't want to record. So let's just make that a dot. Okay, so you can see that we've started to add in columns, which obviously made our data set quite a lot bigger. But it does mean that the format has become larger, so that the number of columns is increased based on what we want to share in terms of our variants. And so you might have a different organism which maybe hasn't been annotated yet, so we don't have that gene column, or you can't, you're not interested in the protein chain, so you don't want to store that. So straight away we can already see that might become an issue, because when you kind of load this into R or want to do any filtering or have any scripts, these columns might actually not be in the data. So if you've built a script based on this exact specification of columns, where I guess H is sample 1, sample 2 is I, and sample 3 is J, and so on. If you then go to a different file, which is a different number of columns, that script is going to fail, and you're going to have to change it, and it's going to be difficult. So we need to come up with a solution where, I guess, the format of the data allows you to store different things but keep the same number of columns.